what we're going to get into is we're going to get into chapter 2 here. And chapter 2 concerns us with our atomic theories and kind of our background information for atoms and molecules. And so we're going to start this off by looking at some key historical ideas. And so if we go back to the earliest days of science, the earliest days of science were a field that we wouldn't think of being scientific these days. It's the field of philosophy. In fact, scientific discourse has its roots in philosophy, as do a lot of different discourses and a lot of different things. And so the key players in the philosophy realm were the Greeks. And the Greeks in particular that we're talking about here are Democritus, who lived and did his writings in the 5th century BCE. And then probably the more contemporary ones, people have names that people have heard of in Plato and Aristotle. And so the reason we bring up these two in particular is that Plato and Aristotle held one particular idea, and that one particular idea was that there is no such thing really as matter, in the sense that there is no defining particle of matter. There is no defining piece of matter that if we break an object down enough times, we get to this fundamental it. Whereas Democritus did believe that. And Democritus believed that so much so that he gave that fundamental it a name. And that fundamental it he called the atom. Or more, appropriately for the Greek, atomos. And so you've got these two viewpoints that are kind of juxtaposed against each other. Democritus 100 years earlier, Plato and Aristotle 100 years later. And ultimately, with the fall of the Greek and the Roman societies, these works become largely lost. The concept itself of science gets lost in the shuffle too. And what we end up seeing instead is that science in general really takes a back seat to a number of different fields for hundreds of years. And in the time of the Renaissance, when the ancient philosophies, the works of the Greeks and the Romans get brought up again, we see these again, but the work of Democritus really gets largely ignored in the face of what Plato and Aristotle did. And so, for the most part, what we see instead is, well, we see a whole lot of nothing as far as advancement is concerned. And so, for that nearly 2,000 years between the 4th century BC and the 1600s, very little happens in the way of atomic theory. Yes, there are some scientific discoveries. Yes, there are some advances in medicine and other areas, but they're relatively low and they're relatively small. Most of the work that is done in those times is in the biological sciences or in the astrophysical sciences. You think about, Galileo and his telescope. You think about, in this age, you start to get the workings of Sir Isaac Newton in Britain. And that's kind of it for a long time. As we get into the later 1600s, Isaac Newton and the work that he did in England brings about a revolution of sorts for the ideas of scientific thought, scientific discourse. science starts to get added again to the curriculum of a lot of really prominent organizations, institutions of higher education, and labs start popping up in places. And the labs start popping up with new technologies. And the new technologies help to innovate technique and start to show that, after all, you know what? Democritus is kind of right. There is a fundamental particle. There is a fundamental it. And that fundamental particle gets called the atom in his honor because he more or less called them atoms himself. But even at that point, we still don't know what atoms are other than just these fundamental particles, and we have no idea what they're made out of. And it isn't until the 19th century, so now we're getting into the 1800s, a man by the name of John Dalton takes some of the scientific laws, some of the scientific principles that are out there at the time, couples them with some observations, and uses them to develop a full atomic theory. And so that full atomic theory consists of 4 postulates. And a postulate is just a statement of fact, essentially. So there are 4 fundamental postulates, 4 fundamental facts that make up the atomic theory according to John Dalton. The first is that every atom is, or excuse me, every element is made up of atoms. An atom is the fundamental particle of all elements. And so every element is made up of these atoms. Okay, so far so good, not that bad. Not too terribly difficult to think about, but kind of revolutionary for the time just because he's stating it as a matter of fact as opposed to a matter of opinion or theory. Second postulate. All atoms of a given element are identical, but atoms of different elements are different from each other. Again, from our viewpoint here in 2020, that seems like a kind of a duh statement. Well, yeah, of course elements are going to be, if I'm looking at gold, all the gold atoms are going to be the same. And if I'm looking at lead, all the lead atoms are going to be the same. And the gold is going to be different somehow from the lead. That makes a ton of sense to us now. But that needed to be stated explicitly, because if you think about in this time, look at postulate number 3. Atoms of one element cannot be changed into atoms of a different element by chemical reaction. Can anyone think of what scientific practice is being directly challenged with that statement? Okay, White just said it in the chat. That's absolutely correct. It's alchemy. Alchemy is still largely being practiced in the 1600s. If you're not familiar with what alchemy is the process, or at least the believed process, that you could turn one element into another element just by manipulating it somehow. And the most common practice, if you at least remember from some of your early history in the Middle Ages, was the idea of turning lead into gold. Sounded great on its face, but theoretically and practically impossible to do. And so the atomic theory of Dalton here explicitly goes after and says, no, that is impossible. You cannot do that. You cannot have alchemy. And so that's challenged in postulate number 3. The other thing that you can point to here is that atoms are not created and they're not destroyed in chemical reactions. And then the 4th postulate, the 4th thing that you look at is when compounds are formed, It's because different atoms are combining with each other. Different elements are combining with each other. But if I look at a given compound, it is always going to have the same relative number and types of atom. And that's going to be the case regardless of circumstance. So when I have a compound, it's going to be because I got different elements coming together. But every single compound is going to have different numbers, different kinds of atoms here. So those are the four pieces, the four postulates of the Dalton atomic theory. Before we move on, I want you to think about these, and I want you to look at the four postulates that we just explored. And I want you to go back to that post lecture that you did, I guess it was 2 nights ago. You had law of constant composition, law of definite proportions, law of multiple proportions, law of conservation. Each of these four is linked somewhere in these statements. And so what I'm going to do, I'm going to lay out here and let you guys kind of talk through it and see what you come up with. And so I'll give you a hint. First and foremost, postulate number 1 here is just a statement of fact. It has no theoretical roots in any of the laws. But the other 4 can be drawn from these 3 postulates 2, 3, and 4. So, like I said, I'm going to lay out here. I'm going to mute my mic actually so that you guys can talk. And let's see what you come up with for how those laws fit. So go ahead and start talking.
I feel like number 4 is definitely number 4 because all the laws, all the laws when they are in a chemical reaction, the element, if I'm saying it right, the element has to stay the same as far as I can't describe it, but I know it's number 4.
I think what he's asking is which law corresponds to which statement here. I believe that's what he's wanting.
Let me see.
So I would say number 4 would probably be the law of definite proportions.
Okay, I got it written. Okay, you said law of
That's what I would first think that one would at least be related to.
Okay.
And then I believe that point number 4 is the law of multiple proportion.
Oh, you think it's the law of multiple proportion?
Yeah, because you combine 2 elements in different proportions. Same thing as the compounds are formed when atoms of different elements combine.
Oh.
I mean, yeah.
Yeah, go ahead.
No, that's right. That's right.
Yeah, because in my notes I put for my homework, I said that the law of multiple proportions is when 2 elements combine in different proportions, or one of the element differs in different ratios. And then for this one, it says compounds are formed when atoms of different elements combine.
I put the different ratios part, and then I put the elements combined part. I was saying that it'll result in the small ratio.
That's good. I don't know. I'm kind of torn between the 2.
What did you say it was?
I think it's the law of definite proportions, because that has to do with the compounds, and they always have the same proportions of the elements that makes up that compound.
same relative number kind of atoms. It's a proportion
I,
by
th- I,
what?
th- I think the law of multiple proportions has to have two masses of one element and one mass of another element. But the first mass can always be reduced back to a whole number.
Compound always has the same relative number and kind of atoms. I thought that it was multiple proportions because when you combine it, the number has to equal. It has to be the same amount on both sides. It has to equal the relative. It has to equal the same amount on both sides. That's how I'm looking at it. It says same relative number and kind of atoms.
I think the key word with the law of multiple proportion is that it has to have two masses of one element and one mass of another element.
That one mass of another element, I felt like that's the result of the two. Or am I wrong?
I'm not 100% positive on that.
Covers in a compound, you have the same particles of the element have the same mass ratio.
I can at least say number 3 is going to be the law of conservation of matter.
Yeah.
So we can at least rule that one out.
And that was
I believe the law of constant composition is point number 2.
Law of constant composition.
The compound, you have the same particles of the element.
Okay.
Identical, but atoms of different elements are different from each other.
Can we agree on that one?
Yeah, let me just take a look at that real quick.
Okay, I'm going to step in here.
Okay.
You're debating very well, and
Okay.
and I'm really good to hear the conversation here. The fact is, number 4 is both.
Oh God.
Okay.
Oh, it is.
If you look at the first statement,
Mhm.
compounds are formed with different elements combined.
Yeah.
Mhm.
That is law of multiple proportions. What that is saying is that when you get two different elements coming together, you can form lots of different compounds.
Okay.
The law of definite proportions is the second half of that statement.
Okay.
The same number and kind.
Okay.
Okay, it's both.
Okay.
Both are in there.
I thought definite proportions is 2.
To what?
The number 2.
Oh, the second statement.
Oh,
Yeah.
I put that in as constant.
that's more aligned to constant composition. Yes.
Okay.
Now, constant composition and definite proportions are very, very similar to each other. So it's easy to kind of put one in for the other. But we tend to think of constant composition in terms of atomic composition, whereas definite proportions usually comes into mass ratios of one element to another. So constant composition can apply to atoms and to compounds. Definite proportions only applies to compounds.
Okay.
And then number 3 should have jumped out. That's conservation.
Yeah.
Yeah.
Okay. Really good conversation. I'm glad to hear that you are all thinking your way through these, because it makes a pretty big difference if you're willing to kind of look at it from multiple kinds of perspectives and go from there. So let's get into a little bit of expanding. So Dalton's atomic theory was proposed in the 1600s, and that is still largely the prevailing theory. In fact, if you look at any of those statements, there really weren't anything in any of those statements that you would look at and go, well, wait a second, that's not quite right. Now, from a standpoint of the nucleus, from some of the things that we know now about subatomic particles. Some of those statements are true to the most part, but there are little tiny things that we could probably pick in them and say, well, if we just change this sentence to say this instead of that, it would still be correct. And largely that comes about because it isn't for another couple hundred years that we actually start to discover subatomic particles. That is, particles that exist in smaller quantity, or excuse me, smaller dimension, things that make up atoms that show that the atom isn't actually the be all and end all. It's not the particle that is the smallest that defines everything else. In fact, there are smaller particles inside of an atom that help to define what that atom is. And so the first of these discoveries is 1897, a man by the name of J.J. Thomson, working in the Cavendish Laboratory in England. And if you are interested at all in scientific history, there are a great number of really, really important discoveries that are done at the Cavendish Laboratory, which I believe is associated with, it's either Oxford or Cambridge. I think it's Cambridge University. And that laboratory actually still exists to this day. It's one of the most prestigious laboratories in the whole world. Working at the Cavendish, J.J. Thomson, in 1897, starts working with cathode rays. Now, cathode rays had been known for quite some time. It was known that when you hook up materials to an electrical power source, that a beam of light, or at least what was thought to be light, shoots out of these materials. And so cathode rays, experiments with cathode rays were done largely in these phosphorescent evacuated tubes. So you had a tube where we take out all the air, so it's essentially a vacuum on the inside. You hook up these materials, and then you put it to an electrical charge of some kind, and the electrical charge generates these cathode rays, and they get sucked into the vacuum, and you get this beam of greenish looking light that comes through. Now, what was interesting and what the Cavendish was working on is a lot of work was being done. Not a whole lot of explaining was being done. There just wasn't a whole lot of information out there. But what Thomson starts doing is he starts playing with, okay, well, what if I change the cathode and the anode? What if I change the materials? Does the beam change at all? And the answer was no. What was really telling was once he hooked in magnetic fields and electrical fields, he found that the beam of light was actually bending consistently in one direction. It was beaming toward the North Pole in the magnetic fields. It was bending toward the positively charged plate in the electrical fields. And light doesn't do that. Light doesn't care about magnetic field. It doesn't care about electrical field. It is going to behave consistently regardless. If you take a laser beam and you point it at your wall. If you take a magnet and push it into the beam of the laser beam, it's not going to change the position of that laser beam. It's not going to change where the beam hits the wall. Same thing with an electrical field. It doesn't work that way. So what this leads Thomson to assume is that this beam of light isn't actually light. It's got to be some sort of particle material. And not only is it a particulate material, it's a particulate material that has to have a charge. And the reason we know that is because if it's charged, then magnet and electrical fields are going to work on it. And we know that it's negatively charged because it is drawn toward the positive plate and away from the negative plate. Remember, opposite charges attract, like charges repel. So he does a whole bunch of experiments. starts to play with the different values of the electrical fields themselves. And what he's able to calculate is that there is a relationship between the mass of these particles and their charge. Now, he doesn't know what the charge is. He doesn't know what the mass is, but he knows the relative ratio of the two against each other. It's called the charge to mass ratio, or the mass to charge ratio, depending upon what reference you look at. And so what he's actually talking about here is what we would later come to know as the electron. And so the electrons, those negatively charged subatomic particles, these are the ones that are going to be influenced. These are the ones that are going to be working here in this scenario. And now we have a ratio of mass and charge for them. We just need somebody to identify one of those objects. And if we can identify one of those, then through calculation, we could figure out what the other one is. And so lots of experiments get done, and most come to agreement that it's probably going to be the charge that is going to be the easier of the two to define. And Robert Millikan, about 10 years later, 12 years later, starts working with an experiment in this really weird looking contraption here. This is the oil drop experiment. Now, in the oil drop experiment, he's got this big steel case. And the big steel case has a really simple design. There's an atomizer here on the top. An atomizer is basically a spray bottle. But unlike the spray bottles that you would use to, put disinfectant in, or window cleaner or whatever, this forms a really, really fine mist. So if you can think of like those old-timey perfume bottles, where they've got the big alabaster flask and this big rubber ball on the end of it, and it just sprays this really fine mist. That's the kind of atomizer that's being used. And so Millikan's using this atomizer, not for perfume or for disinfectant or for water. He's using oil. And so what's happening is this is getting a really fine mist of oil up in this upper quadrant, this upper zone of this apparatus. Now, in the bottom part of the apparatus, we've got these large plates that are charged, electrically charged. So there's a positively charged plate on the top, there's a negatively charged plate on the bottom, and in the middle of that positively charged plate, there's a tiny hole drilled into it. And that's so that the oil droplets can fall very, very finely through that hole. And so we have a limited number of oil drops coming through the hole at any given time. Once they can come through the hole, Millikan blasts them with X-rays. X-rays are a form of ionizing radiation. And so you've got this big hydrocarbon molecule of the oil droplet, and you've got ionizing radiation coming at it. And so the ionizing radiation rips some electrons, causes some electrical charges to be deposited on the droplets themselves. And as they continue to fall via gravity, the electrical plates can be ramped up and control the fall of these based upon repulsion. And so what Millikan is able to do, he can play with the charges on the plates. He can look at the microscope and see how the oil droplets are being affected. Are they being slowed down? Are they being slowed down a lot? Are they being slowed down a little bit? And he can tie that to how much charge is in the plates to get an idea of how much charge are on the droplets. And what he finds is that there's a consistent number. That consistent number, the one that seems to kind of be the number that keeps getting distilled in the droplets themselves, is the Coulombic charge of 1.602 times 10 to the negative 19th coulombs. Now, the charge there is negative because the electrons are negatively charged. But this number, 1.602 times 10 to the negative 19th coulombs, that is the charge of an electron. And now when we couple that with the Thomson charge to mass ratio, we get that the mass of the electron is 9.109 times 10 to the negative 28th grams. So Millikan's experiment takes Thomson's work, finds a piece of the puzzle that was missing before, and then uses it to figure out both of the things that were wanted, the charge of the electron and its mass. And so putting together these two ideas, we end up with a model of the atom, a theory for how an atom is actually constructed. Remember, Dalton's atomic theory didn't tell us what the atom looked like. It just said and kind of described what the atoms were and whether or not they made up all of matter, which we know that they do. The Thomson model, referred to as the plum pudding model, gives us this sphere and says, okay, this is the atom. The atom is this positive sphere. And inside of this positive sphere, we have a whole bunch of these little negatively charged electrons. And so when we hook it up to electricity, because these little electrons are just kind of distributed through this, the force of the electrical current is able to pop those out and give us that beam of electrons that we saw in the cathode ray experiment. But the positive matter here, well, it's just this present goo. It's just there aren't any other particles. There's just these electrical particles kind of shoved in this positive matrix. And so that's the plum pudding model. Now, we know that the plum pudding model is incorrect. But based on the evidence of the day, this is the prevailing model. This is the prevailing theory behind atoms. Around the same time, we saw in the Millikan experiment that X-rays were being used. Well, along those same lines, radioactivity is starting to become uncovered around the same time Thomson is doing his initial experiments. And while others are working in the Cavendish on that, there are some prominent French scientists, in particular Henri Becquerel and his colleagues, Marie and Pierre Curie, you may have heard of them, that are working with radioactivity. And what they find out about radioactivity is that we've got this spontaneous emission of some really high energy radiation and particles. And the radioactivity primarily comes in two forms, at least two particulate forms. There's beta radiation, which are basically high energy electrons, and there's alpha radiation, which are these somewhat heavy subatomic charged particles that are about the same size as a helium nucleus. And this work gets used for probably one of the great fundamental experiments of its time. And so this is something called the gold foil experiment. Now, I'm going to give you a chance to talk again here, and then we'll talk about the results of the gold foil experiment. Then we'll take a short break. Let's think about this. We've got this piece of gold foil, and around this gold foil, we've surrounded it with this ring of photographic film, and in the opening of that film, we've put an alpha decay source. So again, remember, alpha decay is giving us these high energy particles that are about the size of a helium nucleus. And so these high energy helium nuclei are being shot at this piece of gold foil, and the photographic film is showing where the alpha particles end up. And so what I want you to do, again, I'm going to lay out here and let you kind of talk. Based upon that plum pudding model, where would we expect to see these particles go? And so if anyone wants to, I'll allow anyone who wants to draw on the slide here to help illustrate what you guys are talking about. Someone just send a request to do that. But otherwise, I'm going to mute myself here and just let you kind of talk for a couple minutes. All right, so go ahead.
Are you talking about like when the particles like bounce off of something? Is that what you're talking about, or something else?
Yes. So the alpha particles are being sent in through the lip of the foil here. Where do they go once they encounter the foil?
They should go
But
up
I think some of them go like
and
in
down.
like
Oh,
the gold foil, and then some of it bounces off the foil and goes like off of it.
I was thinking it spreads up and down, but let me look back at the model, the pudding model.
yeah, I'm gonna say since it's an alpha particle, it's gonna go through it. It's
I'm sorry, I had to pull up the slide. I need to go back. Could we draw on it? Did somebody request to draw on it?
we can.
Okay, when y'all say that it'll go through it, are you talking about the yellow, like the yellow?
Yeah,
You
the
think it just go
gold.
straight through to the other side, or will it stay in the yellow?
I think
goes like fully through.
Yeah, through the gold.
Okay. Sorry, it took on the okay. Okay, I'm gonna still stick with my up and down. I don't think it'll go through. I'm gonna still stick with the up and down. I'm always the one and then be wrong, but I'll just stick with it won't. I just feel like it'll go up and down. Like it won't. It will pass through the gold. Oh, okay. Well, I think that's 3 out of 1. It just won't pass. It goes straight through and hit the back. It will pass through the gold and hit the blue film opposed to the alpha source. Okay, well, that's 3 against 1. So, okay, it'll go through it.
Okay, so is this what is my drawing what you're predicting?
Yeah, that's what they're saying. Yeah.
Okay.
Through the
And then
gold,
from
yeah.
that blue, it goes outwards, like back to different directions.
Okay, so Malaz, you're adding that some of them will go like this.
No, like from the blue, it like like bounces off back.
Okay, well no, the blue's photographic film.
Oh, okay, never mind then. Yeah.
The blue's photographic film. So once it hits there, basically all it's going to do is it's going to light up on that spot.
Okay. Yeah. Then your drawing is right.
Okay. And so if the plum pudding model is correct, then that's pretty much what would be expected. But that's not what happened. This is actually what happened. So if we look at this particular model, what we see is that the alpha emitter shoots out that beam of alpha particles, and most of them do what was expected. Most of them go straight through. And if we look at the plum pudding model, that makes sense. After all, the only things that are really in there that would possibly deflect them are those little tiny electrons. And we know that electrons don't have a ton of mass. In fact, the electron has, about 1/1800th of the mass of a proton. So you're taking something like helium, which is probably about 7,500 times more massive. And if it encounters an electron, the electron's just going to move out of the way. And most of those would go through. But that's not what happened. What happens is that, a lot of them do go through, but some of them deflect. And some of them really deflect, where that beam hits and then some of them come back to the screen almost in the same direction that they came. And so that leads Ernst Rutherford, the man who devises this experiment, to say, well, hold on a second. This isn't what we expected. And so we know some of what Thomson said was true about electrons, but maybe that's not how his model isn't the way that they actually work. And so Thomson loses the plum pudding model. Rutherford devises a different model that's more accurate, more correct. And this eventually gets developed into our more modern atomic theory. But overall results, we see that there is a dense middle in that atom, and it's really high in mass, because if it wasn't high in mass, if it was just, small, then those alpha particles would have, brushed them out of the way too. But the fact that in the case of gold, we've got something that's, 60, 70 times bigger than a helium nucleus. When the helium hit that, pow, it gets sent back. The helium gets deflected instead of the gold. And so what that tells Rutherford is that there are these heavy dense centers in the nucleus, and that heavy dense center has a positive charge. Again, the reason for that is we know that if it was negatively charged in the center, the positive charge on the alpha particle would have come attracted to it. So we're getting minute deflections in the positive direction because the nucleus is positively charged as well. And so what we come up with is basically the theoretical foundings for protons. And so we know that there's a center, a dense heavy center of every atom. That dense heavy center contains in it protons. And the majority of the rest of the atom. So why is it that the majority of the particles still went straight through? Well, it's because even though we have this really heavy dense center, the majority of the atom itself is essentially empty space that is occupied by these electrons. And so the proton gets named as a result of the experiment. James Chadwick, about 12 years later, devises a similar experiment that helps to show that there are neutral particles inside of the nucleus as well. And so these lead us to the nuclear atom. And the nuclear atom tells us that we've got a nucleus. That nucleus is that dense, positively charged center of the atom. And it's about 1/10,000th of the volume of the atom itself. And so that means that the other 9,999 10,000ths is empty space, or at least space that is potentially occupied by electrons. And since electrons don't have very much mass, alpha particles and other heavy things would pass right through them. Inside of that nucleus, we have two particles. We have the proton, which is positively charged, and the neutron, which carries no charge. And we can see here in our scale model, the overall radius of a typical atom is somewhere between 250 and 300 picometers. The actual size of an atom itself is, 100th of a picometer. At least in the case of gold. For smaller atoms, it's even smaller than that still. And so from a sense of scale, you can really see there's a big scalar difference here as far as volume of that nucleus compared to overall volume of the atom. And when we take it from that perspective, we can start to see, okay, this is why the gold foil experiment went the way that it did. And so let's stop right there. Let's take a 10-minute break. We'll come back in about 10:20, 10:25, and we'll talk about atomic mass units and a couple of other features from the periodic table. But everybody stand up, stretch a little bit, and we'll come back to this, okay?
Okay.
So let's get back into our discussions here with talking about some ideas of things that we would find on the periodic table, and then we're going to talk about atoms and that conversation a little bit more explicitly. So when it comes to the periodic table, we can think about an individual atom in terms of its mass, and there are really two ways of describing it. We can talk about it in terms of atomic mass units. Atomic mass units are usually used to describe atoms in terms of individual atom masses. And then what we'll see at the end of this chapter is we'll talk about what if we're talking about larger quantities of atoms, and for that we're going to get into moles, molar masses, and units that we can actually measure, grams. But atomic mass units, all mass is a relative value, and like I said at the top here, one of the interesting things about science in general is that a lot of it has philosophical roots. And one thing that I remember from my days as a student and kind of looking at things from perspective of learning about the history of science and of scientific discourse, really kind of shook me was the whole idea that every unit is made up. Every single unit of measurement that exists because somebody defined it at some point in time. And so mass is no different. We can talk about things definitively now, because what we've done is we've agreed collectively that this is what a gram means. This is what a pound means. But everything has to start with something. And so for mass, that something is the definition of carbon-12. Carbon-12 is defined as having a mass of 12 atomic mass units. And carbon-12 is so defined because it is a perfect 6 protons, 6 neutrons, 6 electrons. And the mass of 6 protons and 6 neutrons collectively is 12 atomic mass units. Now, atomic mass units are sometimes referred to as Daltons. This is very uncommon, but it is something that you might see more often, especially here in the United States. We just call them atomic mass units. Overseas, you might see that come up a little bit more as being called the Dalton instead. But that's what it is. And so one atomic mass unit is 1/12 of the mass of a carbon-12. And so how we can define all of the other atomic masses is relative to how much does it weigh compared to carbon-12. That's how we do it. And from there, we can kind of go, okay, well, based upon averages, that a proton weighs this much, a neutron weighs this much, and the neutron is just slightly larger than the proton is. And we kind of can go from there. And so from that standpoint, if I look at protons, neutrons, and electrons, what we see, we're going to introduce some symbology here in just a minute. That symbology, we'll explain what that means in just a second. But the atomic mass of a neutron, again, just over 1 AMU, just slightly larger, again, larger in the 4th significant figure than the proton. And then the electron is tiny. This is just a little bit more than 2,000 times, a little bit less than 2,000 times smaller. Think the exact mass, like 1/1820th of the mass of a proton or neutron. What we will often do is, instead of looking at these masses from the standpoint of what is their atomic mass, what is their gram mass. We're going to think about them in terms of mass numbers. That is, for protons and neutrons, we're going to think about them in terms of relative. Relatively speaking, protons and neutrons weigh the same thing. And electrons, well, next to a proton or a neutron, they weigh pretty much nothing. And we do the same thing with charge. Instead of thinking about charges in terms of, it's this many coulombs, what we can think of is, okay, the proton and the electron have the same charge, just opposite signs. It's a lot easier to think of protons and neutrons as being +1 or -1, or excuse me, protons and electrons as +1 or -1, as opposed to +1.60218 times 10 to the -19th coulombs, -1.60218 times 10 to the -19th coulombs. Because once we get into larger atoms, where we've got 20, 30, 90 of these things, that charge is going to be really difficult to talk about. But, there are 90 positive charges and there are 90 negative charges in that atom. Well, that's easier to wrap your brain around. You have a better chance of getting to that and understanding it a little bit more simply. So that's why we use relative values instead of the actual values for their charges themselves. Now, there's one other thing that we really want to talk about today, and that's the idea and the concept of an isotope. Now, isotopes have been known to exist for quite some time, and one of the ways that we were able to actually prove their existence is through an experiment just like this. So, in this experiment, this is very similar to what we saw in the cathode ray experiment. This is very similar to what we saw in some other experiments as well. But what we see here is that we've got this beam of charged particles. So what we did was we took neon and we ripped an electron off of it. And so this beam of neon ions gets pushed into this electric field. And what we see is that it bends based upon the influence of the electrical field. And so the beam here toward the bottom is lighter because the field is going to have a greater impact on a lighter object than on a heavier object. And this one that's not as deflected as much is the heavier. And so they do some analysis. They find out that this beam here is 20 AMUs. This beam here is 22 AMUs. And two things come out of this. Obviously, we've determined that there are multiple isotopes of neon, but we've also determined that one of those isotopes is far more present, far more abundant than the other. And that's an important thing to look at. So in looking at this, you can say, okay, this one's more present, this one's more prevalent, but it's not alone. And so when the data actually gets analyzed, we find that 90% of those have a mass of 20 AMU. That beam that was getting bent significantly is 90% of the atoms. The spot's 9 times bigger than the other spot for the 22 AMUs. This presented an interesting dilemma to the scientists of the time, because again, didn't know a whole lot about neutrons, but we knew that the substance itself, neon, actually was neon. It there wasn't anything else to it. It looked like neon, it behaved like neon. So we knew it was elemental neon, but it wasn't the same atomically. And so we had to produce this idea of an isotope, the fact that elements can take on slightly different forms so long as they hold the same thing in common. And that same thing in common is the number of protons. If the number of protons is consistent, it doesn't matter how many neutrons there are, the relative properties of that nucleus, of that atom, are going to be close to the same. Now, what we'll find out at the end of the term is that having different numbers of neutrons can actually play a significant role in the stability or lack of stability of an isotope, and also in terms of its rarity. And so unstable nuclei become the basis for what we would largely think of as radioactivity. But in terms of isotopes themselves, well, we know that isotopes can exist. It just means that inside that nucleus, we have a consistent number of protons, but we have a differing number of neutrons, and the number of neutrons that are present or possible is slightly different for each case. Now, an individual isotope carries another name. We can sometimes refer to it as a nuclide. So nuclides are specific isotopes of an element. So we would call the two different isotopes, the two different nuclides of neon, we would call them neon 20 and neon 22. And we would write them out in one of two ways. This would either be written out as neon 20 like that, so we can either write it out as the element name itself with its mass number, or the elemental symbol with its mass number. And so both of these ways are useful in helping us to describe individual nuclides if we were studying one versus another individually. Another way of depicting nuclides is through a symbolic kind of structure. And so the symbology here is relatively simple. In the symbology here, what we have is our atomic symbol, depicted here by the letter X. And so this one's not going to change regardless of the isotope. If we're looking at isotopes of helium, this will always be He. And if we're looking at isotopes of helium, the Z number here will also not be changing because Z is the atomic number. And so Z and X are always going to be telling the same story. They're always going to be telling the same thing. The atomic number dictates the symbol dictates the atomic number. It's always going to be that case. Now, what makes a nuclei, or excuse me, an isotope is its mass number, because the mass number is ultimately the thing that can change. And the mass number is just the number of nucleons, the number of protons and neutrons in that nucleus. One of the most common mistakes that students make is assuming that mass number and atomic mass are the same thing. The atomic masses that you get on the periodic table, those are all averages. They are all average masses based upon all the different types of isotopes that are out there. And that'll actually be the subject of Monday's lecture, is talking about those different isotopes and the different things that they can do and how they affect the masses on the periodic table. But mass number itself is just a count. It's always going to be a whole number. It's always going to be a number between 1 and 200 something. Because that's always the nature of what a mass number is. It's a number of protons plus the number of neutrons. So it's always going to be a whole number. It's always going to be something counted. Now, in this particular drawing, there is one other thing that is missing. Now, one other thing that is missing is some of these will actually have something in this area right here. Charge. And that the charge can always be found by taking the number of protons minus the number of electrons. So oftentimes, especially for radioactive materials are often charged in some kind of way. And so it's not uncommon to see them charged, usually positively charged, if we're going to be perfectly honest. But it can go in a number of different directions. And so that location in the top right quadrant next to the X, that's where you would find the charge. And if you need to know what the charge is, or if you need to use the charge to figure out the protons and electrons, that's the formula that you use. Charge is equal to protons minus electrons. And so if I have more protons, I'm going to have a positive charge. If I have more electrons, I'm going to have a negative charge. If they're the same, obviously it's neutral. It's going to have zero charge. So with that in mind, take a couple of minutes and using this format that we just had. Actually, let's do this one together. Let's do this one together, and I'll let you do the next one kind of on your own here. For 6 protons and 7 neutrons. So for the element with 6 protons would correspond to carbon. And so since it has 6 protons, my atomic number is going to be 6. Mass number is my protons plus my neutrons, so 6 plus 7, which would give me 13. And so the appropriate format here would be for carbon 13. And then I could label it, this is not what was being asked, but that is carbon 13 or C13. All right, for the second one, I have 95 protons, so I'm going to put in my 95. 146 neutrons. Okay, 95 plus 146 is 241. Right? And so to identify that, I need to pull up a periodic table or find one if I've got one handy. I'd look behind me, but I'm actually sitting in front of the element number 95, so I'll just pull one up on my iPad here. Let's see, element number 95 is americium, Am. So this is Am, americium. And again, the way we can identify this is americium 241 or Am 241. All right. Any questions about either of these two?
No.
Mm-mm.
No.
Okay. Okay, so let's clear this off. There's one more problem. I want you to work on this kind of. You can talk through it if you want. As we get to things, we can start to add them in. But go ahead and work your way through this. If you got a piece of paper or something nearby, go ahead and just kind of sketch these out. And we can talk about them. Again, if someone wants to request a screen share I'm sorry, to annotate here, I'll be more than happy to let you draw on this and share it. But if you just want to kind of talk it through, go ahead. I'm just gonna, again, I'm gonna lay out here and let you work a little bit.
I'm drawing it out. I'm sorry. Yeah. I want to say the first one's RH, but as a symbol.
For the first one?
Yeah. RH.
With 21 protons?
I thought you added 24 and 21, you get 45, and then the 21 goes on the bottom.
I got SC.
Yeah. For the first one, the protons will never change for the element. The adding of the protons and neutrons will change.
Okay,
So,
I did look at SC, but I thought that, okay.
yeah, so I don't know if you have your book or not, but it'll pretty much tell you how the boxes are laid out. So since 21 will never change, just find 21 on the periodic table.
Okay.
You are on the right track with that first one. Scandium SC is the correct symbol. Just as a reminder, it's the protons, it's the atomic number that drives the element, not the mass number.
Okay.
For the last one, if the neutrons can change and electrons can change, how do we identify the last one?
So we're going to have to assume that since we aren't told anything about charge, that these are all neutral.
Okay, I got you.
All right, any insights on the second one?
Yeah, that one is probably going to butcher this. Yttrium.
Yeah.
That's pretty close. There's some debate about it. It's either yttrium or yttrium.
Okay.
All right, so how does the rest of the table fill out in slot 2?
So the protons will be 39. Oh, and then you'll just have 89 minus 39 for the mass, or for the neutrons, sorry. So it'd be 50. And if we're going to assume it's neutral, we would have 39 electrons.
All right, so far so good.
And then for the last one, I got phosphorus.
Me too.
Yes.
Okay, so if it's neutral, we should have 15 protons. What would our mass number be?
31.
31.
31.
All right,
16 and 15.
okay, and our atomic number would be
2.
15 again. And so we've got, finish off our symbol here, 31 and 15. All right, so that's it. Any questions about atoms or isotopes, or anything else that we've kind of talked about today?
No, I just got to look over some stuff.
I just want to verify something. So really the only difference in an isotope is just going to be its weight. It's literally just going to be the neutrons, and the only thing it changes is the weight, right?
Yes. Now when we talk about nuclear chemistry,
Yeah.
it'll also get into the it'll affect its stability, whether it's a stable atom or a radioactive atom.
Okay.
But in terms of this stuff, yeah, it's just
Okay.
going to affect its weight. It's not going to really affect its chemical properties at all. It's not going to affect its physical properties at all. In fact, honestly speaking, you won't even know it's there.
So it doesn't like affect the way that it behaves.
Other
Okay.
than its nuclear stability, no.
Okay.
Because I mean, right now there are radioactive particles inside of you right now.
Yeah.
You're breathing in, carbon-12 and carbon-13, and probably a little bit of carbon-14 as well. It makes no difference to you from a bodily standpoint, from a metabolism standpoint. The only thing that would be affected is if you had higher concentrations of carbon-13 or 14, they are radioactive. They could play a role in certain systems playing games with you, but honestly, even those, the half-lives of those are so low.
Okay.
They really make no difference. I mean, carbon-14 decays by half every 5,720 years. So really the only impact that comes off of that is when you die.
Okay.
And people who dig up your bones 20,000 years from now to figure out how we lived could use that to figure out that you died 20,000 years ago.
Okay.
In terms of its chemistry, no. Really no difference at all. And in fact, we use that to our advantage. We'll talk Monday about average atomic masses.
Mm-hmm.
The average atomic mass, the masses on the periodic table, we know that when we take a scoop of sugar or baking soda or we draw out some vinegar, there's going to be a mixture of isotopes in there. And what we have going for us is the fact that there are so many atoms in those samples that the differences just kind of even out over time. And that's why we can use those average numbers on the table pretty reliably.
Okay. I do just have one other quick question, not to confuse anybody here. But if we can take neutrons and electrons away from an atom, why can't we take a proton away? I know it would change its element, but what's keeping that from happening?
Well,
I know that kind of gets kind of into alchemy, I guess, changing something is.
Electrons are outside of the nucleus.
Yes.
Electrons are the things that are interacting, and they're relatively low mass.
Mm-hmm.
So if you provide enough energy, you can remove electrons, and it's really not that big of a deal.
Yeah.
Protons, I mean, Chadwick's experiment, you had to use pretty high energy radioactive materials to pop those neutrons out to show that they actually existed.
Okay.
So it wasn't a trivial matter. And in fact, where we find free protons and neutrons usually are in stars.
Okay.
So there aren't a whole lot of those free protons and neutrons outside of nuclear sites and cosmic kinds of interactions. You're not running around and finding free protons and neutrons just kind of walking around today.
Okay.
The other thing that you have is inside the nucleus. The nucleus is held together by a phenomenon known as strong nuclear force. And that's what binds the nucleus together and keeps it from flying apart.
Oh, okay.
Strong nuclear force is pretty significant. It's difficult to overcome. It's actually, when we talk about nuclear at the end, we'll actually get into the derivations of this. But if you're familiar with the Einsteinian equation, E is equal to mc squared.
Mm-hmm.
That is the generation of the energy that puts together. So basically, if you add together all the protons and neutrons that go into a nucleus, the individual proton and neutron masses collectively are greater than the mass of the nucleus that they form. And what happens is that as they go from this disparate collection of particles to this tightly wound together nucleus, they experience what's called a mass defect. And that mass defect is what gets converted into energy. That energy gets released by the nucleus as it comes together. And that is the energy that would need to be overcome to break the nucleus back apart into its subatomic particles.
Okay, I got you.
And so, as you could imagine, on an individual atomic basis, it's probably not that much. You're
Mhm.
not talking about it. You're not talking about massive quantities of energy because you're talking about very low values of mass. But in a collective sample, if I've got a mole of these things, that's going to be a ton of energy that I have to put in to get it, and the results are not going to be, trivial. It's going to be like the nucleus is exploding. It's not just going to be, okay, I'm going to throw off a proton here or there, and that's going to turn my element 82 into element number 79 for gold. Those processes are catastrophic processes. Those processes that we use to get it are usually nuclear involved, and we do some sort of bombardment to make the nucleus unstable, and the unstable nucleus breaks apart. And if gold was the result of that, it'd be gold that you wouldn't want. It'd be radioactive gold.
I got you. Okay, unstable.
Yeah, it'd be very unstable. It would have to go through a series of nuclear reactions to get back to stable. So yeah, you're talking about a bit of an aside here. That's getting us a little bit ahead. We'll talk about that stuff in late June. But
Okay, no worries.
but no, it's a reasonable question given what we were talking about today with all of those discoveries. It would seem that, oh well, if it was that easy to isolate the neutrons, why couldn't they isolate the protons in the same way? Well,
Yeah.
I mean, they could, but the results wouldn't be exactly what you're thinking. They'd be radioactive particles themselves.